We will continue with our discussion on the performance analysis of Emery digital modulations based on constellations in 2 dimensions, right? Examples of which being QAM, QPSK, in general Emery phase shift keying, and many others, right? A variety of constellations. And you might remember we had I think just about discussed the fact that in this kind of a situation basically the receiver uses a single match filter whose output at the sampling instant, assuming that your outputs are really Nyquist pulse shapes, at the sampling instance these are essentially Gaussian random variables. These ULs are Gaussian random variables whose mean depends on the specific point that was transmitted and whose variance depends on basically the characteristics of the noise output of the match filter. Basically it's a complex variable. So is this in the 2 dimensions. It's both these points are in a complex plane, and this is a random variable whose components are uncorrelated, and since they are Gaussian also independent, right? Each component having a variance of n0 by 2. So this is the model with which we will work, and this model corresponds to this kind of a picture for the conditional density function of the x and y components or the real and imaginary parts of the match filter output, given that a particular symbol was transmitted, given that a particular symbol C sub I was transmitted, right? So suppose C sub I corresponding to this point, then the mean of U sub L is this point A sub L, all right, and the density function that is described has this mean and essentially a normal density function in two dimensions along x and y, real and imaginary, right? And therefore this kind of a density function, a 2-dimensional Gaussian density function, right? Similarly for any other point in the constellation. This is a picture depicting the case for 8-array PSK, 8-phase shift keying, right? This is where we stopped yesterday. Do you have any questions about this model which is relevant here? Is it clear that this is a relevant model to work with for analysis of 8-array PSK or in general 2-dimensional constellations, analysis of 2-dimensional constellations? Okay. So basically what do we have to look at? We have to define, of course, the error event in this case also, and as you can well see, essentially how does a receiver decide which point is the most likely transmitted point? By looking at whether the received U sub L lies in the corresponding decision region or not. Suppose you transmitted this and the corresponding decision region, let's say, is this, then if your received U sub L lies within this sector, we are considering the case of 8-phase PSK here, then we will of course make the correct decision, or else if it lies in some other sector, that describes the error event for this situation. You actually transmitted this, but you received U sub L, this value, because of the noise here, gets modified vectorially and takes this vector A sub L and modifies it to some other vector U sub L in some other sector, right? So this is your, let's say, the true vector. The noise may take it here, bring it here, and now you will wrongly decide that this is the point that was transmitted, right? And so on. It could, depending on how the noise 2 components behaved, you could have gone into any sector with different probabilities. So if the picture is clear, then the analysis is fairly simple and straightforward to carry out. So how do we define our P sub E? Let me, before writing the expression, I have plotted in more detail here the density function around a specific point. Let's say this was a point that was transmitted, right. This is the same A to E PSK situation. The density function is shown over here. It's a two-dimensional density function, and therefore it's a three-dimensional picture here. And these two shaded lines define the decision region around this point, right, for the A to E PSK case. And as you can see, the density function has spills over outside this sector, right, and it is the spilling over outside this sector which gives a finite probability to the error events, right. This tent like shape does not, its span or its base is not restricted only to this sector, it extends outside this sector, right, and the volume under this density function which lies outside the correct decision region sector contributes to the error probability. This is what you must really appreciate in this picture, right, and therefore we must really evaluate what is the volume under the tails of this distribution function such that it lies, I have shown two planes here, either above this plane or to the left of this plane. I have shown two planes. Let me call this plane B, this plane A, right. This line B divides the plane into two half parts to the left of this line. That is why I have shown this shaded region to the right of this line, right. This is the top half and that is the bottom half. So the volume of the density function which lies outside this sector can be thought of as consisting of two sets of such tails. One, integrate the density function to the right of this plane, right, and the other to the left of this plane A, and then if you add these two results you will get the total volume, except the fact that the volume under this sector, this wedge like sector will be computed twice and added. We should have only done it once. What we are interested in doing is computing the volume of the tail of this density function which lies to the right of this line B on this part of the plane, right, because that is outside your decision region. Similarly, to the left of this plane which also lies outside the domain of your decision region, right. Now you could have directly added these two results and obtain your total error probability, except for the fact that the volume of the same density function under this sector will be computed twice, because it will be computed as part of this plane, this half plane, as well as part of this half plane, right, whereas you should have really computed it only once. So strictly speaking, you could compute the volume on this right half plane, on this half plane, the volume on this half plane, and subtract out the volume under this once. That would give you the exact result, right. However, it again we will assume that the signal to noise ratio is sufficiently high so that the error that is encountered by counting this probability twice is negligible. As you can see from a typical density function that I plotted here, that the volume, the tail is really going to peter out quite a small value by the time it reaches this kind of a sector, which is quite away from the basic point, right. So the volume under this sector is going to be anyway negligibly small. So whether you count it once or whether you count it twice is not going to make a terrible amount of difference to your result, and therefore we will take recourse again to the union bound argument and say we can think of the error event as the event corresponding to the received point lying to the right of this line or to the left of this line, without worrying about this area being counted twice. Okay, so this is a basic approach for performance analysis for this kind of situation. Is it clear? Now we can proceed with the analysis. So your P sub E is the integral of the 2D density function over the portion of a complex plane which does not include the decision region. That's the basic definition. Right? This is how we define error probability in this case, that is, compute the integral of that two-dimensional PDF on that portion of the complex plane which does not lie in the decision region. And one can evaluate this either numerically in the way that I just suggested, or we can use that union bound argument that we just went through. So obtain a union bound. Fortunately, this in this particular case, this bound is quite tight, right? It's quite reasonably a very good approximation to the actual value, because we expect the volume over that wedge to be very, very small. So counting it once or twice hardly makes any difference. But strictly speaking, P sub E will be equal to the integral over the half plane B. Remember, this is the half plane B, that is to the right of this line B. That is the half plane B, right, of the xy plane. The xy plane has been divided into two halves by this line B, right. So it's equal to the integral over the half plane B plus the integral to the left of half plane A, okay, minus integral over the wedge, which is a region of intersection of these two planes on the other side, right. It is this which we are going to ignore in the union bound, right. So this is the true value of P sub E, and the union bound basically will ignore this third term because it is rather small. Is it okay? I have just re-explained what I explained earlier purely in words. Okay. So the important thing then is to try to evaluate the volume of under this density function in one of the half planes, because in the other half plane it will be similar, right. We must find out how to evaluate this volume in one of these two half planes that we have been talking about. Is there any doubt there? Speak out if there is some problem there, we can discuss it. Okay. So the question is, how do you compute this volume under this half plane, any of these two half planes? And for that I have the following result. Suppose we have a density function. What is a density function we are concerned with? It's a density function in two variables, x and y, Gaussian density function. Both the variables x and y have a variance sigma square, so it will be simply, or there will be no square root, right, because the product of the, so please ignore this square root, it is 1 by 2 pi sigma square exponential. Now where is this density function located? What is its mean value? Let us say some mean value x bar y bar corresponding to A sub L, right. Let us call this some mean value x bar y bar. So x minus x bar whole square plus, both of them have identical variance, plus y minus y bar whole square, this whole thing divided by 2 sigma square. Mind you, this is not the most general form of the Gaussian density function. I hope you are familiar with the most general form. What is the most general form? There is also a cross correlation term between x and y, right? In general, if x and y are not independent, then the joint Gaussian density function of two random variables involves a third term which requires you to use the correlation coefficient rho 1 2 between x and y, which in our case happens to be 0. So that term does not come to the picture. This is from your basic knowledge of Gaussian density functions, which I have not done in this course, but which I am presuming you all know. Okay, but in any case we don't need it here, right? All we need is this form of the density function, joint density function of two independent Gaussian random variables, which is simply obtained by the product of the corresponding individual Gaussian density functions, right? Which is very simple. Whereas if they are not independent, they are not in the product. You cannot factor them like this. These can be factored out. The px and the py can be factored out here, right? But when they are not independent, they cannot be factored out. You know that from your basic knowledge of probability theory. Anyway, that was a digression. So this is the kind of density function we have to work with, and we are interested in computing an expression which is going to be a double integral over x and y, right, of this density function, where the region of integration, I have not specified any limits here at the moment. The region of integration is going to be one of the half planes that we discussed, either A or B. Okay. Now then this will be of course twice, right? Yeah, we assume, because we are taking a symmetric situation here, and the result is, suppose this distance, the distance of this mean point to this half plane is d by 2. Okay. So if I draw a perpendicular from here to this, and suppose this mean value is at a distance of d by 2 from the corresponding half plane, outside which you want to compute, or on which the the particular half plane on which you want to compute the volume, then value of this p sub e is 2 comes from the fact that you are doing two such computations. Q function with an argument of d by 2 sigma. Okay, that's the result. This factor 2 comes because you have to compute over two different half planes, identical situations, but on any one half plane the value of this integral is this value. Let's see how. Have you understood the result? We are going to see how to obtain this, but have you understood the statement of the result? Because that's the starting point. To understand how this comes, let's look at this picture here. It's the same picture as this. It's really the same picture. There is not much difference, except that I have not plotted a three-dimensional form of the density function here, but shown the density function in the form of contours of constant value, right? So I have just shown it like that. So these are the contours of the density function pxy. This is your mean point corresponding to x bar y bar, and therefore your d by 2 corresponds to this. Actually this picture is not very nicely drawn. This y should have been drawn parallel to this half plane. Okay. Suppose I want to evaluate the volume under this density function which lies in this half plane. Okay, this is the half plane we are considering. Actually, strictly speaking, this entire half plane. This circle was just a convenience to indicate the points of transmission, right, that your signal points were lying on this circle, right. But actually speaking, as far as error probability calculation is concerned, you have to calculate the volume under this function over this entire half plane, right. Now what I have done is change the coordinate system for representation of the Pxy. The earlier xy was some arbitrary xy here. I am going to first of all shift it here. I am taking the coordinate system to this point, so that the mean becomes 0 0 both along x as well as along. So x bar and y bar both become 0 each. So first I am doing is just a translation of the coordinate system to this point, that makes the mean value 0. The second thing is to rotate the coordinate system so that let us say the y axis becomes parallel to the half plane over which you want to compute the integral. Okay. So obviously the x axis will be perpendicular to this, and then this value will be simply dy 2. The rotation is such that the y axis becomes parallel to the line which defines the half plane over which you want to compute the integral. Alright. Since the line B here is the line which defines this half plane, the y axis is made parallel to this. Actually I should have called them y prime and x prime to avoid any confusion with the previous x and y, but I hope it does not cause any confusion. Then I will continue to work with x and y, right. Now because these contours are circular, it is obvious that if I rewrite the density function in terms of these new coordinates, they will continue to be of the same form. Okay. Now this is pictorially quite obvious. Whether I write the 6 circles along this coordinate system or along this coordinate system, the equations of these circles are going to remain the same. X square plus y square is equal to some constant, right. And therefore the form of this density function does not change as a result of this coordinate transformation, because it is only a rotation, and because to start with these contours were circular. If any of these conditions are not there, then we would have had trouble, right. Actually this is equivalent to saying, just to for those of you who have some better idea of probability theory, or who can appreciate this kind of statement better, see, to start with we have x and y, right. By coordinate transformation what are you doing? You are generating some x prime y prime through a matrix transformation, right. What we are doing is, this matrix is such that it only rotates the axis. So what kind of matrices are you familiar with? Some matrix the unitary matrices, so called unitary matrices are the ones which, yes, cos theta sin theta is an example of that kind of a unitary matrix. Any unitary matrix such that u conjugate, suppose this is u transpose is equal to identity matrix or unitary matrix, that carries out a rotation of the coordinates. Now it can be shown, it is very easy for you to verify that if x and y are independent to start with, and if you transform it by means of a unitary operation like that, then x prime y prime will also be independent, right. So that is what you want to know, that they will be described with the same Gaussian density function. If the unitary matrix has unitary transformation has two properties: the independence of these random variables will be maintained, and their norms will be maintained. The norm of the vector xy will be maintained, that is, the length of the vector will not change, because you are only doing a coordinate transformation.
So I don't understand the concept of the length of the vector.
Okay, don't go into it. I didn't. This was just a just to give you an alternative argument to basically say this, to imply the fact that x prime y prime will be continued to govern by the same density function that we started with. X prime y prime will continue to be independent Gaussian random variables, with each having a variance of sigma square, because we have only done a coordinate rotation.
So that's obvious from the symmetry of the whole thing.
That is obvious from the symmetry of the circular contours that we have, because whether you take sigma along this direction or along this direction or along this direction, its value is same because these are circular contours. If they are elliptical, for example, that will be the situation when rho 1 2 is not 0, or when both of them have different variances, right? Then there will be a problem. But in this case, because they are circular, no matter how you rotate them, the variances along each axis will continue to be the same, and they will continue to be independent. Oh, the shifting is only makes a mean 0. After shifting, I am doing a coordinate rotation, right? So I really gone into 2 coordinate transformations. Number 1, shifting, translation. After translation, I am doing a translation doesn't do anything except making the mean 0. The second coordinate transformation we are doing is rotation. The rotation does not alter the variances along either axis, the new axis, or the fact that they are independent, because it's a pure rotation. Okay. Now this is something, if you are not very comfortable with, I will just suggest that you pick up any elementary text on probability theory, or even the text that you have with your lattice book. These things are dealt with in the review chapter in that book. So just make yourself comfortable, or you come to me, I will explain to you in more detail, because I don't want to spend too much time on this. Alright, so if you have understood this, it's very easy to write down now the expression that we are looking for. Your P sub B is twice, I want to write the integral over Pxy to the right of this plane, where y-axis is like that and x-axis like that. Is it obvious what the integral will be? The x limits will be from d by 2 to infinity, and the y limits will be from minus infinity to plus infinity, right? The entire y-axis span is being taken, but the x-axis span is going from d by 2 to infinity. That's all. That's all you need to appreciate. So you have this value. Right, x goes from d by 2 to infinity, y goes from minus infinity to plus infinity. Okay. Now the rest is all very easy. As far as y is concerned, I can factor out the y portion of the density function 1 by root 2 pi sigma e to the power minus y square by 2 sigma square, and integrate it separately. The value will be 1. So I can totally ignore that. So what I am left with is 1 by root 2 pi sigma e to the power, and that's precisely what you define the Q function, right? Your Q function is defined precisely in terms of this integral, except that this is d by 2. So it's d by 2. By definition, this is the result. Okay. So this is how this result comes. Very easy to appreciate it. Let's study it a little more for the special case that we are really discussing, namely the 8-array PSK, 8-phase PSK. Okay. Okay. For the 8-phase PSK, any questions before I proceed further? Is this clear? How we obtain this result? So we have, mind you, this is slightly less than the most correct result. Less than, okay, it is greater. Okay, what I meant was it is not really the exact result, right? It's a union bound. Yes, the actual probability will be less than this quantity. So this value is slightly greater than the actual probability, but it is for reasonable signal to noise ratios, it is very, very accurate. It's good enough to, you might as well take it as the exact result. Okay. So the bound is quite tight for large values of EB by N0. So let's now specialize this result for the case of 8-phase PSK. It's obvious that the overall symbol error probability will be the same as, that is the average error probability will be the same as the error probability associated with any particular symbol, because we are assuming all symbols to be equally likely, right? Equally likely. What matters here is the equal a priori probability of all the symbols.
Also energy would matter. Okay.
Energy is obviously equal, right? But even if energies are equal, if various symbols occur with different probabilities, then we cannot say this, right? The average error probability is the same as error probability associated with any specific symbol, given that any specific signal a symbol was transmitted. So any specific signal point. That is, if I compute the error probability given that a specific signal point was transmitted, and if all these specific signal points have the same a priori probability, then the overall average probability will be, probability of error will be also the same as this, because it will be really 1 by 8 times this plus 1 by 8 times this again, and so on, if all these are same, right? So final result is the same. Okay, now your PSK is described by a constellation in which the points are distributed on a circle. Let's say the circle is of radius a. So let a be the radius of the constellation. Which essentially says that your received signal has an amplitude a, right? What will be d by 2 in this case?
What will be divided by?
Because d by 2 is a crucial parameter here, as you can see.
A sin pi by 8, sir.
Hmm?
A sin pi by 8.
That's right. It's quite obvious, so I don't have to explain this at all. It's a sine pi by 8, right? Because your sector around each point is described by an angle of pi by 8 in either direction. Total angle is pi by 4, 2 pi by 8 is pi by 4, and pi by 8 is a half angle, which turns out to be 0.3827a. Also, from your match filter theory that we have already discussed, your output a by sigma square is given in terms of the pulse energy and the noise power spectral density function, 2EP by n0, right? So your union bound, then if you substitute these results, so from there you can get d by 2 sigma as 0.3827a by sigma, right? And a by sigma you substitute from here and you will get this result, 2q, right? It's d by 2 sigma, right? Now a by sigma is square root of this, so I'll put this also under the square root sign and write, I'll ignore this 27, just 0.38 square 2 e sub p by n sub 0. Okay, and this is going to be really nearly equal. One does not even have to write less than or equal to, provided this is sufficiently large. The last point to consider is, this is what kind of probability is this? Symbol error probability, right? In practice, like we did yesterday, we'll be interested also in bit error probability. So how do we go from symbol error probability to bit error probability in this case? Now in this case, one has to keep in mind that in the two-dimensional signal constellation, one will usually do a gray coding, so that a single symbol error causes at most a single bit error in the, at least in the most common situation, where a symbol is mistaken for its adjacent symbol. Of course, if it is mistaken for some other symbol, then we cannot guarantee
So the
that.
probability we calculate is for, is not for just not adjacent symbol.
That is true. You are quite right. The probability that we have calculated corresponds to a particular symbol being mistaken for any other symbol, right? But the major component of this probability comes from contribution from that event, right? Because the values, the contribution by other events, probabilities of other events will be very, very small. It's obvious because for a Gaussian density function, that area under the density function keeps going smaller and smaller as you keep going away from the mean value. So the major portion comes from there. So one does not really worry too much about that second order of error that is taken, that is affected by this computation. So if you keep that in mind, if you are doing a gray coding, let's consider the Atery case. Suppose you mistake a particular symbol for its adjacent symbol. How many bits will go in error? 1 out of 3. So for every 3 bits you will encounter only a single bit error. So essentially that implies that your bit error probability will be this probability divided by 3, right? Also, what will be your E sub p there? Because we have gone from one symbol to its adjacent symbol, right? The gray coding ensures that only one of the bits will go in error, right? That means out of every 3 bits, we are making 1 bit wrong on an average, right? So every time an error occurs, such as error occurs, we are assuming that only single, this implies only a single bit error will occur. Of course, the assumption involved is that errors of the kind in which you go to a non-adjacent symbol have very, very small probability. Therefore, this error probability is largely comprised of errors of going from a symbol to its adjacent symbol. That is the assumption implied here. So there is a further approximation implied here to be sure, right? But that approximation is also, yeah.
Doesn't remain an upper bound.
It is still a upper bound. It is still.
It's difficult to say that, but since it is a second order effect, one doesn't worry about it so much. Okay, it's a really second order effect. In fact, very, very accurate. You are quite right. It doesn't remain the upper bound because you are neglecting certain probabilities.
So, but we are including all that in this.
They two may be compensating for each other, but we don't know how. But, so we will enter into that argument. You are quite right. Okay. I also, before I wrote this expression, I also wanted to substitute for E sub p in terms of E sub b. E sub p will be 3 times E sub b, because bit energy is defined as the pulse energy divided by log 2m, which in this case is 3. So if you do all that substitution, you will get this as 0.88 E sub b upon n0. What was the result for binary PSK? Do you remember? That's a very standard result. You should remember it almost. There is no factor of 2 by 3. It's Q of 2 EB by n0, right? This factor of 2 by 3 is not very significant. More important is what is inside the argument Q, right? Because this will not affect orders of magnitude, whereas that will affect the order of magnitude of the probability, because this is inside that Q function. So roughly, if you ignore this factor of 2 by 3 in one case and 1 in the other case, which one is better, binary PSK or 8-phase PSK? No. For a given bit energy, this argument is smaller. That means the area under the tail will be larger, right? This is a monotonically decreasing function of its argument, right? The larger the argument, the smaller the value of this probability, right? Because you are considering the area under the tail of the density function, Gaussian density function. The farther you go away from the mean, the smaller the value of the area under the tail. Okay? In fact, roughly it is about 3.6 dB poorer than binary PSK. That is, to get the same error probability, 8 phase PSK will require about 3.6 dB more signal to noise ratio as compared with the corresponding value required for the binary phase shift gain. And this is quite understandable, isn't it? Because the noise now has an easy access to adjacent symbols as compared with binary PSK for the same bit energy, right? As you can quite see from this picture. Which picture? Any of them, any of the ones which we discussed. For example, this one. All right, because for the same, of course, this is pulse energy. Your points are becoming closer and closer together, and for the same noise variance, there is a larger probability that one symbol will be mistaken for another symbol. Now, this is therefore quite unlike the Emery orthogonal signals that we discussed yesterday. For the Emery orthogonal signals, as we increase the value of m, and if your signal to noise ratio is above a certain basic threshold value, which is very low, you are guaranteed to get better and better performance with increasing value of m. Whereas in the case of two-dimensional signal constellations, as you increase the value of m, your performance is going to degrade further and further, right? So there is a trade-off involved to choose between orthogonal signals or two-dimensional signals. The behavior is, the reason for the behavior is quite understandable, because in one case you're allowing the dimensionality to explode. For the orthogonal case, there is no as more and more signals are being added, your signal space dimension is increasing, right? More and more. In the other case, the signal space dimension remains fixed at 2, and it is within that dimension that you have to distribute the various signals, right? So in one case we are working with a strictly band limited set, namely the two-dimensional set, whereas in the other case we have no bandwidth limitation, right? Because as we increase the value of m, we are expanding bandwidth, right? It is, we discussed this situation, power limited and band limited situation. The orthogonal signal set corresponds to the power limited situation, not band limited situation. We are assuming that bandwidth is infinite there, right? So therefore they have the potential of improving your performance as you increase the value of m. Whereas in this case your application domain is different. Your bandwidth is a major constraint, and this is what you can trade off, let's say, signaling rate with performance. As you go for a higher value of m, you can improve on your signaling rate, right? Because every symbol can contain multiple bits depending on what is the number of points in the constellation. But the price you are going to pay for is in terms of performance, error probability, bit error probability is going to become poorer and poorer in bit error probability, right? So this is the major thing coming out of this, which was intuitively quite obvious. How much time is there? Okay, there is very little time. There is a further one little result which I would just like to mention here, and the rest of it, a few paragraph or so I would like you to read yourself. I will give you the handouts tomorrow. This is a result for a more general constellation, because this result that we derived for really pertain to Atari PSK. It was derived in the context of Atari PSK, but we could have a general constellation, not in the form of points distributed in a circle. It could be QAM on a grid or concentric circles or any such arbitrary shape. Now the general result is motivated from this special result very easily. Let me first quote the general result. The general result is P sub E is given by n sub m into q evaluated at d min upon 2 sigma. Okay, where n sub m is the average number of nearest neighbors. in the constellation.
D mean is distance between
D mean, of course, we already know it's the minimum distance between any two points on the constellation. Right? D mean is the minimum distance between any two points on the signal constellation. All right. Let's see how this result can be motivated directly from what we have obtained here. See, in this case, in the Iteri PSK case, what was the number of nearest neighbors? 2, one on either side. That defined two half planes over which you have to evaluate the volume under the density function, volume under the tail of the density function, right? Now, if you have more than 2 nearest neighbors, you will have to your decision region will get modified accordingly, and your tails definition will also get modified accordingly, right? Suppose you have a grid, there will be 4 planes which will be bounding the defining the decision region. So the area which will contribute to the error probability will have to be calculated on 4 different kind of half planes, right? Each of them will give you a similar kind of result because of the symmetry of the situation, right? And therefore the result does make a lot of intuitive sense. We are not really going to the exact derivation of this, but intuitively it seems reasonable to expect this kind of a behavior.
Sir,
Yes?
in the more general case, the error probabilities for each symbol would be the same.
That's right. So therefore this is a somewhat
generalized.
it's more of a rule of thumb kind of result than an exact result, right? So with a result which you can almost apply independent of what constellation you are working with. Otherwise, you have to, for each constellation, you have to derive an exact result separately, right? So therefore, this is a nice design result to work with, which does not specifically depend on which specific constellation you are working with, right? So it's a rule of thumb kind of result. I think the rest of it I'll leave you to study by yourself. And as I promised, I couldn't start information theory today. We'll start that tomorrow.